Okay, I promise to keep it brief. I've never seen so many people in this lecture room since the first week of my first year, but I know we're all hungry and want to grab some food. So what I'm going to be talking about today is my fourth year project completed with the multifunctional materials and composites group, which comes under the umbrella of this department, and it's titled Nanomaterials in Revolutionising Diabetes Diagnostics. So I'm sure some of you are already aware what diabetes is, but for those of you who aren't, I'm going to give a brief overview. So diabetes is a metabolic and anti-immune disorder where the body is unable to react to insulin, and that's referred to as type 2 diabetes, or in some cases the body is completely unable to produce insulin at all, and that's type 1 diabetes. Now 10% of diabetics in the UK suffer from type 1 diabetes, and it's important to note that type 1 diabetes, unlike type 2 diabetes, is not brought on by a person's lifestyle. It's something that's inherent from birth, but can also set in later in life. So the number one symptom of diabetes is high blood glucose levels. And if the condition is left untreated, it can lead to several chronic complications. These include cardiovascular disease, nerve and kidney damage, and early onset Alzheimer's. So some statistics for you. 3.2 million people in the UK suffer from diabetes. And as I mentioned, 10% of those people suffer from type 1 diabetes. Of those 3.2 million, 1.1 million of these cases are undiagnosed. So people who are completely unaware that they live with diabetes. Each year, the NHS spends £10 billion on treating diabetes alone. That represents 10% of its budget. So to put that in context, that's £1 million every hour, or just over £300 every second. See how that compares to the alumni account. So 84% of diabetics in this country do not meet the NHS guidelines to reduce their risk of developing those complications I mentioned earlier. And this puts a tremendous amount of pressure on the healthcare system in this country. So clearly, what solution is required? Well, we need better monitoring of diabetes and better diagnosis of the condition. So how do diabetics currently monitor their condition? Three main ways. So through test strips, the finger prick test, and continuous monitoring. And these are vaguely simple and cheap methods. However, they each have their own individual problems. They're either highly invasive. Test strips and the finger prick test require blood to be drawn from the body, so that clearly limits how many readings you can take. And these continuous monitors that are quite prominent on the market are incredibly inaccurate. So what we need is a non-invasive, high-accuracy solution and something that's affordable. So we're clearly not the first people to think of this, and it's been a big focus in the media lately, so we've had some coverage here. So Apple reportedly has a secret team working to develop a non-invasive sensor to measure blood glucose levels through the wrist that it hopes to incorporate in its Apple Watch product. Google has actually developed a contact lens that goes in the eye that measures glucose levels in the fluid within your eye. And we have software companies that claim to be able to use artificial intelligence and machine learning to actually detect glucose just by pictures of your finger, which I'm very doubtful of. But we've yet to see any kind of revolutionary or even vaguely successful technology come to market. So what we in our research group propose to do is measure glucose levels by monitoring the breath. So as you know, the breath contains many gases, mostly nitrogen, oxygen, carbon dioxide, and some water. However, it contains hundreds of endogenous components. Now, these are either contaminants left over from the atmosphere, or they're byproducts of chemical reactions in the body. In our case, one such chemical, acetone, acts as a chemical biomarker for blood glucose levels. There are known correlations that allow us to map the breath acetone level onto blood glucose levels, and these require some calibration, but they're accurate and they're well known. However, the problem with this is the acetone concentration within the breath is extremely low, in the vicinity of parts per million or parts per billion. And up until now, we've only been able to detect these concentrations using large pieces of benchtop apparatus, very expensive equipment. So this is where nanomaterials come into play. So the nanomaterials we've been working with are termed MOFs, or metal organic frameworks. They are a subset of porous coordination polymers, and what they consist of is a metal atom or a molecule encased in a housing or framework of organic linkers or ligands. They are cheap and easy to synthesize compared to a lot of inorganic counterparts such as zeolites. And what's very important is that they have ultra-high porosity. To put that into context, if you take 2 grams of such a material, the internal surface area would extrapolate to about the equivalent area of a football pitch. And we'll see where that comes into play later. And over the past 10 years, we've seen a lot of research and investment in these materials. We've seen over 20,000 unique MOFs cited, with a huge range of applications from catalysis, chemical sensing, drug delivery, and many more. But our MOF here, developed at the department, is termed ZNQ at OX1, which is simpler than it sounds. So what it is a zinc-based guest atom, so the atom here that sits inside the framework, and that's a zinc quinoline atom, and that sits within our patented and developed here at the university OX1 framework. And what's unique about this material is that it exhibits a highly selective photoluminescence effect under UV when exposed to acetone. So the zinc quinoline is the light-emitting molecule within the material, and the actual effect of being put within this framework actually enhances its light-emitting effect. It's cheap to synthesize, which is important from a commercial perspective, and it has low temperature operation. So this isn't the first material that has been cited in papers that can react in this way to acetone. However, it's the only one that can react at low temperature. So this is due to carrier mobility. So a lot of other materials in this field require high temperatures to induce the carrier mobility to exhibit photoluminescence. However, in our material, the carrier mobility is actually intrinsic to the material. This material operates at room temperature. And other potential applications include low-power LEDs and tunable chemical sensors. So this isn't solely restricted to diabetes. So here we have some images of our lovely material. So this is actually the first time we've worked with such a material in crystalline form. All other research of these kinds of materials have been done in solution. So we have the struggle in coping with measuring this material as a solid. So we had to think about how to deposit this material and how to deposit it in such a way such that it didn't inhibit its chemical properties. Here on the right, we see a molecular packing diagram with the solvent accessible volume highlighted in yellow. So this is where the analyte, in our case acetone, actually enters the framework. And here we have a molecular structure of the material. So as a sensor for acetone, what our material exhibits is a high sensitivity to parts per million levels of acetone. And this is due to that incredibly high surface area I mentioned previously. It has high selectivity for acetone. It will not react with any other components beside acetone. And that's unique of these kinds of materials. And very importantly, it reacts reversibly, or partially reversibly. If the acetone is vacated from the system, the material will return to a neutral state. And it exhibits high chemical stability, which is also important from a commercial perspective. So we have our material. We introduce acetone to it. We see 2 effects. We see a wavelength shift of around 35 nanometers and a signal quenching that we can actually see here. And this effect is so powerful that we can actually see this with our naked eye. So we introduce acetone and we see this color shift from a pale cyan to a lime green, and that's reversible. So clearly, in the real world, as I'm sure you all know, nothing behaves in a nice linear way. So we've dedicated 1 year to collecting over 100,000 data sets pertaining to this material and tried to develop a model of the material. This data pertains to acetone response, so how it responds to that acetone, what the various wavelength and quenching correlations are, had response under repeated use. So we've put this material through dozens of cycles and see how it changes the way it reacts and how we can model that. And importantly, the steady state response. So how quickly it reacts to the acetone and then how quickly it returns to a neutral state. So clearly, as part of our study and the engineering aspect of the project is developing the sensor equipment. This is one of the setups we actually devised. So it consists of a modulated UV source that's introduced to the sample that's enclosed within a sealed environment, and that yields two data streams. We have a differential amplitude output, and that's yielded through some optically bridged photodiodes, passed through a diff amp and a lock-in amplifier, and then we have our salient wavelength yielded through an optical spectrometer. And we use these two data streams in tandem to tell us exactly how much acetone has been introduced to the sample. So as part of developing these setups, we've run into a lot of problems and we've had to optimize a lot of factors. One of those was the actual excitation frequency. So 365 nanometers is a lot of energy to be introducing to a solid sample, and we saw rapid degradation in the sample. So we actually managed to introduce the wavelength to 405 nanometers without reducing any resolution in our system, which was quite a big deal and took us a lot of trial and error to get. And we've developed a 3D printing, we've 3D printed an environment where we can uniformly dose acetone. And as Lionel said, there's been a big focus in the department towards 3D printing, and it was great to be able to actually 3D print something and use that in the project, and something that worked out for the best. And we've developed this entire setup to be scalable. Nothing exists here that can't be shrunk down to a portable piece of equipment that could be considered from a commercial perspective. So this setup is able to detect part per million levels of acetone. So conclusions. What we have in the department a patented material that can detect acetone concentrations at part per million levels. And that clearly has very interesting applications in the field of diabetes. It exhibits selective behavior, which is unique to these kinds of materials, and it can sustain repeated exposure cycles. It reacts and recovers within a few nanoseconds, and it actually recovers within a few minutes, which is suitable for our application. And very importantly, it responds predictably to temperature, and we can control all the factors, and we have the models that correspond to these. And this, for example, is one of the models we derived that corresponds to the multi-cycle response of the material. And we have a number of models like this for each of the aspects I mentioned previously. So what's next? So we're currently in the process of securing funding for a full-time postgraduate study of this material. This will hope to enhance our understanding and consolidate our model of the MOF. At the moment, what we have is data at parts per million level, but really to attain the sensitivity required for commercial applications, we need to go down to parts per billion, and that requires more expensive bespoke technology. Evaluate options for mass production. This would be the first time such a material has ever been mass produced, and figure out how to scale down this setup. And finally, start thinking about how to incorporate clinical trials. And we've been speaking with people in industry on how to do this. So clearly today I've skipped over a lot of the detail, and I couldn't talk about everything I wanted. But if you are interested in learning more, feel free to read the paper we published. That's available on our group website. I believe my poster is outside, or please feel free to find me later with any questions. And finally, I'd like to thank my supervisor, who helped me a great deal in this project. Thank the engineering department, and especially Eva, for organizing everything today. And finally, to you, the alumni community, for granting me this prize and for inviting me to speak, and for being so patient. Thank you very much.
Sam, that was a fantastic lecture. It was really, really well delivered, very informative, superb example. And I'm delighted that you're the first winner of our alumni prize, because you're clearly a very deserving winner. And you're tackling a problem which is really at the heart of the interaction of engineering with society. Diabetes, big problem. I know, I've got type 2 diabetes. And I remember the shock of when it was discovered. I underwent something that was mentioned in your lecture called the prick test. And the nurse who delivered it said, "Oh, well, you're okay there." I said, "What do you mean? Does that mean I'm not one or what?" You misunderstand the nature of the test, she said. Warmest congratulations, Sam. That was a brilliant presentation, and I hope you'll answer questions for people outside when you're standing beside the post that you've got outside. I'm really delighted.
Thank you.
Our
Thank you
first
very
winner.
much.
Warmest congratulations.